Welcome to a refresher lesson for polynomial functions graphing. This video corresponds to the examples on a worksheet packet that can be found at my Teachers Pay Teachers store. In this video, I will explain the skills and steps necessary to complete all of the examples on the worksheet. Please feel free to skip around to engage in the concepts with which you would like some help. So when we are looking at trying to graph polynomial functions, we need to consider some characteristics or behaviors that will occur with the graph of the function. And the four that we're going to focus on with our graphing today will be to find the y-intercept for our function, to identify the x-intercepts, to also identify the multiplicity at each of those x-intercepts, and then to determine the end behavior, what's happening on the right and left ends of our function. Now, I don't want to take the time to go through this table in detail. This is also on the worksheet, but if any of these terms are unfamiliar to you, go ahead and pause the video for just a moment and read through the description before we move on. All right, so let's take a look at this example. We are being asked to graph the polynomial function f of x equals 2 times x minus 3 squared times x plus 1 cubed times x plus 4. Now notice I don't have a graph here at the moment because what I want is to identify those characteristics and behaviors first, and then we will use that information to graph. So let's start with the y-intercept. The y-intercept happens when we put 0 in for x into the function. So we are going to be finding f of 0 to see what our result is. So we'll have 2 times 0 minus 3 squared times 0 plus 1 cubed times 0 plus 4. So that's going to be a 2 times, this will be negative 3 squared, which is 9, times, this will be 1 cubed, which is 1, and then our 0 plus 4 will be 4. So if we take 2 times 9 times 1 times 4, we get 72. So our y-intercept will be the point 0, 72. Next, we're going to look at x-intercepts. Now for x-intercepts, we want the values that will give us 0 as a final answer. And because we have a function that is in, factored form, right? These are all factors being multiplied together. Then that means that getting a result of 0 depends on any one of these factors becoming a 0. So if I can get any one of those to be a 0, then my overall answer will be a 0, and that's where our graph will intersect with our x-axis. So I have the factor x minus 3. If I set that equal to 0, that means I have x equals 3 as one of my intercepts. I have the factor x plus 1. When I set that equal to 0, then that means I have an x-intercept of negative 1. And I have x plus 4. When I set that equal to 0, then I will have x equals negative 4 as an x-intercept. Okay. Now, along with those x-intercepts, we want to look at something called multiplicity. The multiplicity refers to how often are we using that factor in the polynomial function. And that is going to be indicated by our exponents. So we have a 2 on our first factor of x minus 3. We have a 3 on the x plus 1. And then we don't really have anything written here, which implies that this exponent is going to be a 1. Now we're only interested in the factors that have variables in them. So we're not concerned about this 2 for the moment because there's no variable involved with that factor. Okay, so each of these x-intercepts came from each of these factors that are now being raised to some power. And based on that power, we have what we call multiplicity. So if we go back to this for just a second, you'll notice here that there are 3 things that can happen with multiplicity. Multiplicity tells us how our graph is going to behave at each of the x-intercepts. So if the exponent is a 1, then our graph is going to act like a linear function, and it will just cross through the x-axis in a straight line like a linear function would. If our factor has an even number for the exponent, then the behavior is going to act like a quadratic or any other function to an even degree. And so it's actually going to touch our x-axis like that x-intercept is a vertex. Okay, and then the third option is that our factor might be taken to an odd exponent that's bigger than 1, right? Because we already had something happening when it was 1. So any odd number for the exponent that is bigger than 1, then our graph is going to act like an odd degree function, and you're going to get that shelf at the x-intercept where it kind of flattens out. So if we go back to our situation here, the x minus 3 factor being raised to the 2 means we have a multiplicity of 2. And that tells us that at x equals 3, for our x-intercept, the graph is just going to touch, like that x equals 3 intercept is a vertex. Then we look at x plus 1. That is to the 3rd power, so that is an odd exponent bigger than 1. So a multiplicity of 3 tells us at the -1 x-intercept, we're going to get a shelf, kind of like a cubic graph would. And then finally, x plus 4, that's being taken to this 1 exponent. So that has a multiplicity of 1. And that means that our graph is just going to cut straight through the x-axis at 4 like it was a linear function. Okay, last but not least, we're going to look at end behavior. Now with end behavior, we don't really care what's happening in the middle of the graph, so to speak. We're only interested in what's happening to the far right or to the far left. And the notation we use for that is to say as x approaches negative infinity. So this is saying if we go to the far left of our graph, what is f of x doing? Okay, what is our graph doing? Is it going up or is it going down? As we go and take x to positive infinity, then we're talking about looking at the far right of our graph. And again, noticing what's happening with our f of x's. Is my graph going to be going up or is it going to be going down? Okay, now this is all determined by two things. We need the a value, which is what we call our leading coefficient of the function. And we need to know the degree of the function. Okay, what is that highest exponent? Now, if this was in standard form, that would be easy. We would look at the leading term. We would pick out the leading coefficient. We would look at the exponent on that leading term, and we would have that information. But in factored form, it's not quite as obvious. So here's how we determine those things in factored form. So let me just erase some of this so it's not too confusing and doesn't get too messy for us. All right, so here's what we're looking at to get this in factored form. For the a value, you are going to look at any constant factor that you have. You are also going to look at the variable term in each of these binomials. Now, in this case, each of the binomials, the x is by itself. There is no numerical coefficient with x. So if you can imagine trying to actually multiply all of this out to get it into standard form, then all of the x kinds of terms that might possibly give us that leading term, they're all going to be taken to a power. Again, this one is just 1. But if there's no number in front of the x, if it's just a 1, then 1 to any power is still just going to be 1. So in this case, we don't really have to worry about those variables inside of the binomials. And that means that only this constant factor is going to contribute to what a is going to be. So a is going to be 2. Now, let's say for a second, just off to the side here, let's say that f of x had been the 2 here, but then we had a 2x plus 4 or something like that being squared. Then you would have to take this full 2x and square it to get 4x squared, and then multiply it by that 2 to get an 8 for your a. Okay, usually it doesn't get quite that complicated, but if it does, that's how you would handle that. Okay, all right, so in this case, again, we're only concerned about that constant factor, so our a is going to be a 2. Now, for the degree, again, if you think about multiplying everything out, you would be taking this. Let me again just erase some of this so that we can see what we're doing. Sorry about that. There we go, back where we need to be. So again, if you were trying to multiply all this out, we don't want to actually do that because that's a lot of work. But if you were trying to multiply this out, you would be taking this term to this power, and then you would be taking this term to this power, and then this term to this power, which again is just a 1. And then you would have to multiply all of those together. And so the shortcut here for figuring out what the degree of this polynomial is to simply add up your exponents. Because the biggest possible thing you're going to get from each binomial is that first term raised to that power. And then when you multiply all of those together, you would just be adding the exponents. So that's what we're going to do here. We're going to take the 2 plus the 3 plus the 1 to get 6, and that is the degree of our polynomial. Okay, so with that information, we can go back here to this table. And in this table, we can see we're interested in the exponents on this side, whether they are even or odd, and we're interested in the a value across the top, whether it's positive or negative. And depending on what combination we have, that will tell us what's happening at the ends. So we have a positive a value with 2, and we had an even exponent with 6. So we're interested in this cell right here, which tells us that as x goes to negative infinity, so on the left side of our graph, f of x is going to go to positive infinity. So our graph is going to go up. As x goes to positive infinity on the right side of our graph, f of x is also going to go to positive infinity on that end as well. So both ends are going to be going up. Okay, so here, as x goes to negative infinity, f of x went to positive infinity. As x went to positive infinity, f of x went to positive infinity on that side as well. Okay, so now we have a lot of information to work with. And now we can go and try to actually graph this. Now keep in mind, when we are graphing polynomial functions, because they are complicated, we want the best estimate that we can get. It is not going to be perfect. Okay, but doing this by hand, we want to get a pretty good idea of what this is going to look like. So we start with our y-intercept. Notice that our intercept was 0, 72. I do not have 72 blocks on my y-axis, so I'm going to need to adjust my scale. Now, what I do have on my y-axis is 6 boxes going positive and 6 boxes going negative. So in order to make this fit, I am going to use a scale of 20. Okay, and then in the negative direction as well. That way I'm sure to make 72 fit in the y direction. Now, I don't need to go very far left or right because my intercepts were 3, -1, and -4 on the x-axis. So I'm going to keep those at 1 for my scale. Okay, I do not have to change both scales in order to graph. So change whichever one is necessary to make things fit. All right, so my 0, 72 is going to be right about there. That's where my y-intercept is going to be. Then for my x-intercepts, I will be at a +3 right there, a -1 right there, and a -4 right there. And then remember with the multiplicity at +3, I expect to see my graph touch. At -1, I'm expecting to see a shelf. And at -4, I'm expecting it to go straight through. Okay. And then with my end behavior, I know that this end is going up as I go negative infinity, right? Negative infinity to the left. My graph is going to positive infinity. So my graph should be going up on this side. And similarly, it should be going up on this side. As I go this direction to the right, I'm going to positive infinity for x's, and my graph for y's is going up. Okay, now that's a lot of information, and I should have a pretty good idea of what this is going to look like. but in case there's any gaps in the information. So maybe, for example, here between -4 and -1, I want just a little better idea of where my graph is actually going. I can use test values. So I can pick something like x equal to -2, put that into my function, and work out what that answer is. Okay, and it ends up being a -100. So I would expect at -2 that my graph goes through this point right here of -100. Okay, so any place where you feel like you have a gap or you would just like a little better idea of what's happening with your graph, you can do these test values. But now let's try to put all of this together and see if we can come up with a reasonable estimate of what this graph looks like. So we know at -4, it's going to go straight through, and to the left of -4, my graph is going up. So I've got a graph that looks like this, and it's just going to cut straight through, and we know we're heading down to this point here. Then as I come and get closer to -1, I need a shelf. So I need it to come up like this, and then kind of do a cubic shelf that looks a little bit like that. And then I'm heading to my y-intercept, so I'm going to hit that 72 right there. And then I have to get over here to 3. So this must have turned around somewhere to get down here to 3. And remember at 3, I'm just touching like it's a quadratic. So I'm going to come down, touch, and then head back up, which makes sense because my graph is supposed to go up on the right side as well as the left side. And so that gives me an idea of what my graph should look like. Okay, so you're taking in and determining all of this information, these 4 characteristics and behaviors of y-intercepts, x-intercepts, multiplicity, and end behavior. And then you bring all of that together and use that to estimate your graph. If you missed anything in those steps, feel free to rewind and rewatch any part of that process that you need to. Now, before we finish for today, I also want to show you an example of going the other way. In some cases, instead of them giving you the function and asking you to graph it, they will give you the graph and ask you to find the function for it. And we're still going to use those same characteristics to help us do that. So in this case, we're actually going to start with the x-intercepts. Okay, looks like we have an x-intercept right here and right here. So we have 2 of them. And if we look at our scale, it looks like every line is a scale of 1. So we have an x-intercept at x equals -3 and an x-intercept at x equals +1. Okay. We can also see the behavior of the graph at each of those points. At -3, it is going straight through. And at +1, we've got a touch. So what that tells us is 2 things. First of all, our factors are going to be an x plus 3, because remember the general form is x minus the intercept. So x plus 3 for one factor and x minus 1 for the other factor. And then based on this behavior of going straight through or touching, or if there was a shelf, that tells us the multiplicity, which is related to the exponent. So the fact that this one went straight through means technically the exponent is 1. And since this one touched, that means we have an even exponent. And we're going to assume for these problems that if it's even, it'll be a 2. And if it is odd greater than 1, we'll use a 3. Okay, we're not going to get more complicated than that. So if it's an even, if it appears to be even, we'll use 2 as our exponent. If it appears to be a shelf where it would be an odd greater than 1, then we will just use 3. Okay, so that's quite a bit already. We have factors and we know what power those factors are being taken to. The other thing we need to know, though, is do we have a value, a constant factor involved here? Okay, and the best way to determine that is with a test value of some sort. Now, whenever possible, try to use the y-intercept because it's usually a fairly easy number to identify. However, you cannot use the y-intercept if the y-intercept is 0. So if your y-intercept is 0, then you have to pick some other point on the graph that you can tell the x and y coordinate for. Now, in this case, our y-intercept appears to be right there at 6. So what that means is, in my function, which has a general form of f of x equals some possible constant factor times x plus 3 times x minus 1 squared, if I put 0 in for x, I know from this y-intercept that I should get an answer of 6. So I'm going to work out this part of the equation to see if I need some a value to get the answer to be 6. So I've got an a here. The 0 plus 3 will be a 3. And then the 0 minus 1, which is negative 1 squared, is going to be a 1. So I now have the equation 3a equals 6, which means a had to be a 2. So my final equation, my final function, is that f of x equals a constant factor of 2 times x plus 3 times x minus 1 squared. Okay, so you're using a lot of those same characteristics and behaviors we talked about when you're graphing. The only thing we're really not using is the end behavior because it doesn't really impact what the function is. You could use the end behavior to do a quick check. For example, you can see here that if I looked at end behavior, I would have an exponent of 3, because it would be the 2 plus this 1 here. And I would have a leading coefficient of 2, because these are just x's with no numbers to them. So that means I have a positive leading coefficient, a positive a value, and an odd exponent. And so again, if we go back to that table, oops, there we go. A positive a value with an odd means we've got this happening. So as x goes to negative infinity, f of x goes to negative infinity down. As x goes to positive infinity, f of x goes to positive infinity, which means up. So we can see, yes, as I go to the left to negative infinity, I went down. As I go to the right to positive infinity, I was going up. So that makes sense. That matches. So you could use end behavior as a way to kind of check yourself. But really it's going to be your x-intercepts, possibly your y-intercept, and your multiplicity that's going to help you to write your function. Okay, I hope that you found this to be helpful. If you would like to see other concepts that you need to refresh or review, please check out my Gordon Global Math page on YouTube. Videos covering Algebra 2 and pre-calculus concepts will be added throughout the spring of 2025. Thanks for watching.